We are going to look at the properties of graphs and functions. We're going to define some new terms. First of all, intervals of increase. An interval of increase is an interval of the domain where the y values increase as the x values increase. So an example of a function that has an interval of increase is an exponential function. So let's find the interval of increase. An exponential function looks like this. Notice that if we take 2 points, anywhere on an exponential function, you will always have, for increasing x values, for x2 greater than x1, y2 is greater than y1. So for an exponential, this is true everywhere. So therefore, the interval of increase is the entire domain for an exponential function. This isn't true for all functions. So let's look at another function. Let's look at a parabola. Do we have, as x values increase, do the y values increase everywhere? Well, not everywhere. If we take this section over here, if we compare these x values, let's say this is -2 and -1, the corresponding y values would be 1 and 4. So -1 is bigger than -2, but 1 is smaller than 4. This is not an interval of increase. The function here is decreasing. It's going down. But after we hit the vertex, the function is increasing. So we can say that the interval of increase is x greater than 0. You could include 0 or not include 0. It doesn't really make a big difference here. Intervals of decrease. Well, we just looked at the parabola, and that the interval of decrease is when x is less than 0. What about 1 over x? What are the intervals of decrease for 1 over x? Let's just use this little sketching. Notice that as the x values are getting bigger, the y values are getting smaller. And again, as the x values are getting bigger, the y values are getting smaller. So the interval of decrease must be the entire domain. But remember, x cannot equal 0. Now we're going to talk about end behavior. What happens to the function on the far ends as x goes towards huge negative values, so negative infinity, and huge positive values? What is happening to the function? So we'll start with an exponential function again. So as we get ever smaller values towards negative infinity, The exponential function is always getting closer and closer and closer to the x value, to the x-axis. So we can say here, as x goes to negative infinity, y goes to, what are the y values approaching? They're getting closer and closer to the x value, the x-axis, and that corresponds to a y value of 0. What about here? As x goes to positive infinity, the y values are getting bigger, 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 gigantic. The y values are also going to positive infinity. Have a look at this reciprocal function next. As x goes to negative infinity, again, like the exponential, you can see that the y values are getting closer and closer and closer to the x value. It's from to the x-axis. You can see again it's from under the x-axis, but it's still approaching the x-axis. It's still approaching a y value of 0. So as x goes to negative infinity, y goes to 0. Will it ever actually reach 0? No, it's an asymptote. It's not going to actually touch it, but it is approaching it. So this arrow really means getting close to, approaching. Now let's look at the positive branch. As x goes to positive infinity, what's happening to our function? It's getting closer and closer again. So again, we can say y goes to 0. Another very important definition is an even function. You can say a function is even if when you sub in a negative value, it's the same as when you sub in the same value that's positive. So f at negative x is equal to f at x. A parabola is an example. F at 1 gives you a y value of 1. F at negative 1 gives you a y value of 1. F at 2, let's see what f at 2 would give you. F at 2 is equal to, we're doing x squared, so it's equal to 2 squared, which is equal to 4. F at negative 2 is equal to negative 2 squared, which is equal to 4. So this is a couple of examples of places where it looks like it's an even function. To show it in general, we'd have to show it for all x. So we have to say, let's see, f at negative x is equal to negative x squared. We're just plugging it into the formula x squared. And negative x times negative x equals positive x squared. So this is really just equal to the original function. So if you're able to say that f at negative x is equal to f at x, then that means you have an even function. Another way to define an even function is to see that it has symmetry in the line in the y-axis. So if you reflect it through the y-axis, you would just get the exact same graph again. This means another parabola that's transformed over here, if you reflect that, it would be over here. So this parabola, this transformed parabola, is not even. Only the original one that was not transformed, or maybe some other special parabolas, but in general, not all parabolas are even. Only ones that satisfy f at negative x equals f at x. Okay, one other example I'm going to leave for you to try is an absolute value function. It's even. Can you prove that it's even? How do you prove it? Well, get started this way. F at negative x is equal to, work it out, and you want to eventually show by the end that it's equal to f at x. If you can do that, then you can say that it is even. Let's look at odd functions. The definition of an odd function is that f at negative x is equal to negative f at x. An example of an odd function is sine x. So why is this an odd function? We could look at the graph, or we could do some computations. Either way, we could prove it. So let's look at graphing sine. Do you remember what it looks like? Starts at 0. Maximum of 1 at 90 degrees. Back to 0. Minimum. Back to 360. Okay. So this is what it would look like. Now let's graph f at negative x is equal to sine of negative x. What does this look like? If we go back to our sine function, the original sine function, and look at the negative values, we can use these values to help us. So sine at, if we now sub in 90 for our x value, it will become negative 90, and we will be looking at sine of negative 90. What's sine of negative 90? Well, it's right here, and it's negative 1. So this function at sine of 90 is negative 1. Sine at 0, sine at negative 0 is going to be the same. Sine at negative 80 will be the same. Let's look at sine at 270. This is starting to go upwards to a value of 1. So sine of negative 270 will be up here to complete this line graph. There's some similarities between the original sine function and sine of negative x. If we were to reflect the original sine function first into the y-axis and then into the x-axis, we actually end up getting sine of negative x. So we can see that it satisfies sine of negative x is equal to negative sine of x. Let's look at another example of an odd function. Let's show that f at x equals 1 over x, the reciprocal function, is in fact an odd function. So we need to prove that f at negative x is equal to negative f at x. Let's think about this for a second. F at x is 1 over x. What's negative f at x? Negative f at x would be equal to negative 1 over x. So we're trying to show that when we sub in a negative x, it will get this. So let's start our proof. So f at negative x is equal to 1 over negative x, which is equal to negative 1 over x. We know this from working with fractions over the last few years. So this is the same as negative f at x. So we say therefore f at x is equal to 1 over x is an odd function. Okay, I'd like to show you one more example quickly. So I'm going to erase the sine function. My favorite even and odd functions are the parabola and the cubic function. So the parabola is the even example, and it's easy to remember because it has an even power. Not all even powers are even functions, but it's a nice example. And x to the power of 3 has an odd power, and it just happens to be an odd function. So this helps me to keep even and odd functions straight. So we can prove that this is an odd function. If we sub in negative x, this would be negative x times negative x times negative x. Negative times a negative times a negative is a negative. And it's cubed because it's x times x times x. And this is equal to the exact negative of g of x. So therefore, g of x is equal to x to the power 3 is odd. What does this look like? It looks like this. If you reflect it first into the x-axis, and then into the y-axis, you get the same graph that you originally had. Same thing with our reciprocal function. If you reflect it through, it doesn't matter which order as long as you do both reflections. If you reflect it through the x-axis and then through the y-axis, you get the exact same graph again. So it has this special symmetry. Also, you could think of it as rotating it around 0, 0, 180 degrees. So let's do it again, looking at the rotational symmetry. So if you take this branch here and you rotate it 180 degrees, so this would be like 90 degrees over here. Keep rotating it 180 degrees, it gets to there. Let's do the bottom branch. You rotate that 180 degrees. So let's start with 90 degrees, and then the rest of the way, and it also matches up. So if you rotate it 180 degrees around 0, 0, you end up with the exact same graph again. We could do it with the reciprocal function, and it would also work. Continuous function. A continuous function has no breaks or holes over its entire domain. A nice example is a simple line. It just keeps going continuously. There's some other nice examples. Sine function. Oh, whoops, I didn't make it very sine. Well, this isn't exactly a sine function. Let's just say this is some trigonometric function. It has no breaks and no holes. Parabola has no breaks and no holes. Exponential function, no breaks and no holes. Well, what is a break and what is a hole? Well, let's look. Here is a function that has a discontinuity, the reciprocal function. It's discontinuous at x equals 0. So we look at the graph. It doesn't exist when x equals 0. Why does it have a discontinuity? Well, f at 0 would equal 1 over 0. And in our math, in our number system, you absolutely cannot divide by 0. All of our operations, all of our math breaks down if you somehow define a division by 0. Okay, well that is the end of these terms. These terms are going to come up over and over again in this course, so make sure that you know them and understand them very well. Good luck.